Okay, will this okay, I hope the screen visible. It's is the aspect okay? Okay, great. So yeah, so as I said, I'm going to start with the basics. Okay, let me run you through what I'm going to do in this presentation, and then so we have some expectations. So as you know that doing these kind of talks is difficult because we don't really have free access for all to sophisticated data set. So what I'm going to use is the data set which we all have access to, which is, let's say, the S&P 500 index data for end of the data. You could theoretically pick any other data set which you want, and if the data set which you actually wants to create features out of. So if you have, let's say, access to your daily factor values, your factor values in the sense momentum factor, if you have price to value, you have other sentiment or any other sort of data for each equity or even for the indices. In theory, it would work exactly the same, at least the feature engineering part. But for now on, the emphasis is not on the factor that we have here, but if we have few good factors based on some other prior knowledge, how we can feature engineering them. Don't really bog down that why we have created this factor or that factor, at least in the example. They are all as a dummy for the dummy cases. It's not, they could be meaningful, and I have tried to at least make them meaningful, but it's not a certainty or mathematical financial necessity for them to be. Okay. So if you have access to your GitHub links to the website, you can just see the exactly the same notebook. Let's start from the beginning. So what I really have in this case is normal S&P data which I have. So I can show you it just the normal open close OHLC price data set. So I've not picked any specific date. It's just the end of the day data set we have. And what features what I'm going to say is that I'm going to say if I can with some certainty, or do I'm able to create a model or a forecasting mechanism which can actually predict my next day returns. Effectively, that's the end game that we all have, quants have. So effectively, I have my data set. I've loaded it. It's a simple field, a simple task. This is the price return. So I think it's important to mention that when are you working with indices returns, it's always good to know what kind of return you're working on. Is it a total return index or is it a price return? So price returns would not include returns made on gaining dividends. So obviously, cash indices are not going to have any dividends. Obviously, you cannot trade them, but ETFs and other indices, they would have a different characteristic of having a price return and a total return indices. So it's always good to know your strategies might get varied what kind of returns you have. So the P returns is effectively just that. I've created that into a price return, change the percentage from change. Now go to some feature engineering. Okay, let's so you can read it simply that I've just taken the spider price ratios, and now it's sort of a I would say a like a thinking venture we have to do. We have to say if I'm going to forecast next day returns and I only have my OHLC data set, what ways when can I actually do that? So if you talk to technical analysis or the fundamental or the enthusiast, to those who look at graphs and say, oh, there's a head and shoulder, there's a 20-day moving average, something like that. They will all make a suggestion that okay, there's a 2-day trend, 5-day trend, some moving average is going on above or lower some threshold, something like that. So try to come up with a feature that would be like that. Oh, what if today S&P has made money? Is it going to lose money tomorrow? Or what if the last week it has made money? Is it going to continue on that streak? So some sort of mixture of reversal, which is in financial series, this is evident. There is a reversal. You are making money, you are going to lose money later on, and the other way around. If you are on a streak of making money, you might be on that streak for a longer duration than you anticipate or think. So that's the way I've tried to come up with few features, at least in this notebook. And so I have created those features in like two buckets. So the first, the target is my next day return. We should There should be no doubt about that. That's what we are trying to forecast in this at least case. We have not picked the models. We're just trying to focus on our features itself, and that's what I try to. That's my message is that in financial engineering, it's really difficult to come with features. As Tom mentioned, that risk arb was is a little tricky in the sense that you don't really have clear cutout features for that. You have to read research papers, might have to read some blogs, have to look at more talks by Tom itself to find few features. But once you have those features, they should make some financial sense. That's the first main goal. Mathematically, we will try to figure out if they do that, but they should have a solid financial backing. So what feature that I've tried to come up at least in this scenario is that okay, we are going to forecast next day return. Let's look at what return I have made today. That becomes my feature one. What was the return that I made yesterday? That's my feature number two. What was the return which I made in last 2 days? So I've just taken as the product of all the return of these 2 days. Okay, what's the return that I have made in the last 5 days, which is effectively a week? Okay, what's the return that I made in last 14 days, 22 days, 120 day, and 250 days? So effectively, their proxy 14 days. The reason I put it is that I don't know, people really love 14 as a number when they're looking at technical indicators. Other than that, there's no reason to pick 14. There could be, I don't have any other reason of picking 14. 22 days proxy for 1 month. Like 22 trading days is an approximation you take for in quant. 120 is for a half year, and then 250 is for roughly for a year. So those are my those features. I'm going to say that these are my different features, just based on the past return itself. They might make sense. I'm not denying that they will not make sense, but there's no guarantee for it. Okay, that they will make sense, and that's what we are trying to figure out at least in this feature. Now, in the terms of the volume features, it's a OHLC data set. Let's see if we can have some information based out of our volume also. So what I'm going to say is that I'm going to say that same thing about for the same logic that I had for the returns. I can use the same information and then can take it to volume itself. What information I had in the last previous day volume, 5-day volume, 20-day volume, 1 year volume. So the idea in volume is that an abnormal increase or decrease in volume actually hints to something. It's not necessary indicator of price moving up or downward. One can think of it as a regime shift or it as an indicator of some unusual activity in a stock. That's a really good indicator that we find in some research people do talk about it. So that's what I'm trying to capture. So that's pretty much background information on how I have thought about few features. So these are like dummy features that I've tried to come up with. One thing to note is that you cannot really use the volume as it is itself. It's meaningless number. If it would have been a stock, the meaningful thing would have been to use the turnover itself, which is the total number of stocks divided, sorry, the total volume traded on a given day divided by the total outstanding stocks for an equity. That is a much more useful and comparable across all the stocks. But using volume is itself is not a good idea. It's going to be a huge number, and volumes always have a trend. So if you try to look at here, I've just used the data and the volume. I have just taken rolling 252 is effectively at each given point. I'm looking at the last 1 year volume, taken a total sum of it. You can take a mean also and just try to plot. So what I'm trying to say is that, okay, if I'm going to longer term volume, 1 year volume is still longer in some sense that, okay, if 1 year volume I'm looking at last year, is it remaining in a similar range or there's a trend? You can see there's a clear cut trend. It's on the log scale. Your volume has increased like 2-3 folds in the last, let's say 10, 15 years. So this pretty much itself is very unuseful information. It will not be useful information. So the idea that we have come up with is try to normalize in some ways. Okay, so to make these volume features on some scale comparable to each other. So one can argue about it, but the one way that I could come up with is that, okay, let me just divide it by this 1 year volume itself. So if there's a trend in longer term duration, which is 1 year, probably there's a trend in 20-month or 20-day volume or 15-day volume or 5-day volume. So one can make an argument that way, and that's what I've tried to use is that. So every volume that I have here, all factors from 9 to 14 are actually going to be divided by this rolling sum of 252 days. So they all on the same scale. That's the whole idea. To make them comparable in one way, you can say that. Okay, so now just trying to code out these factors very easily. As I said, that factor one is my previous day return. Factor two is my the return day before the previous day. And then I think we are all aware of the shift function, which is it shift your time series in a sense that so positive shift means you're shifting that factor ahead in time. Negative would mean you are actually shifting it before the time. So the days, let's say before it. You do that, you come up with your factors till point 18 are very simple. So like I'm not using these. So one can also do it through using the close price itself. You can do a shift of close price 252 days before minus, let's say the previous day prices, but it actually breaks into different problems that sometimes the close prices are not adjusted per se. There are cases when you're working with equity and your data vendor might not have given you neat and clean close prices which are adjusted for split, stock splits, or reverse split, something like that. But then they do provide you daily returns, which are effectively what you can use. So as a practice, at least at our fund, we tried not to use returns, the close prices to get back to returns, because it's, as I said, it's a data issue sometimes. In theory, the price return from both should match exactly, but there's no guarantee that the data vendor will not guarantee you that. So to use the daily price return is effectively a better way to do that. That's why I've used that. So there is no saying that this approach is correct, that is correct. They both are exactly the same. Okay, now going back to the return, the feature that I made out of the volume itself, I'm going to say. So I said that 1 year volume is effectively, I said, it's a rolling volume. So the rolling feature is that at a given point, it takes the last 252 days, because it's a time series that I've set out. We sum those and then we shift it out. So there is no lookahead bias. And then I create the features from 9 to 14, effectively following the same convention that I mentioned in this volume features. Now, if you go ahead and look, our data frame would actually have grown to a size which is big. Now we have large number of features in this. Effectively 14 new features we have in our data frame. Okay. So I think if you guys are not aware, there's a great tool to look at these features in some sense, how they compare to each other. So we know that correlation, you can look at it very easily, but you actually wanted to plot them in a single plot and see how they compare. SNS is actually a Seaborn library which has a function called pair plot. So what it does is that it creates pair-wise plots of each factor with each other. So I filter only for features which are factor features. So filter is a function there. You can just filter the column which matches your name of fact. So that's what I did. So from factor 1 to 14, I've tried to pair plot them. So in this example, the idea is not to look at, just to show that if you see that there are few features which are actually very correlated to each other, it looks that they are nearly identical. If you have too many of these features, it might be an issue or might not be an issue, depending on how do you interpret it. So I think as is an example, you can see, I think this feature, I think feature 9 and feature 10 or something 11, they are linearly very good. These are scatter plots, so you can play around it. It actually gives a very neat and very fast way of visualizing how your factors are correlated to each other. You can also add a factor here, which is target. I could have that, and there will be another 15 by 15 grid it will form and show you all the plots. Anyway, there's a small digression. Okay, if I actually try to plot my factors in time series fashion, let's see how does it look like. Then it's always good because our features are anyway in time series fashion. if I actually plot that out, it's easy. It's like I filter my factors. I've said that, okay, I put some figure size, and with these, this is how my features look like. So if you see that from 1 to 8, these are my features which were derived from returns, and the below features are derived from volume. Even by without even using any algorithm or machine learning technique, you can say just by looking at your eyes, you can say, so these features look very correlated. They are similar in sense, and they ought to be. At least in this case, we have derived it using one field or two fields. So but it's really good if you have different features. You would have maybe cross-sectional features. So cross-sectional features. So one thing I wanted to highlight in that time series features mean you have for a single entity going back that feature, it changes every day. Cross-sectional features would mean that for a single entity, it might not change every day. It could change, but the idea is that we are comparing that feature for that stock with the similar feature for a different stock. Get my point? So it's important to plot them in some way. So for time series features, uh, featured like plot like this makes sense. For a cross-sectional feature, something like pair plot would actually make much more sense. But it's always good to see that through both plot and we have really great techniques in easy way of plotting. It's this SNS plot in Seaborn library, and even into two pair plots are very or legend plots, line plots are easy to plot in it pandas also. So that's an idea. Uh, Okay, let's go to some other things which effectively is that okay, how we wanted to see the correlation itself. So yeah, we like to see the correlation, how these factors are correlated. So it's a simple idea of okay, I have a data frame with factors. Factors is all the factors from 1 to 14. You just I filter out the name. I'm going to see the correlation of that data frame, each column with my target itself, and then that's I'm just going to. So one thing I think people are not really aware that you can actually have the correlation. There are two kind of correlations available. uh, there's a rank correlation and Pearson correlation. So by default it actually shows you Pearson correlation, and if you have studied somewhere in your school or college correlation, I am sure it's going to be Pearson correlation, which that's the definition that we all probably are aware of. Rank correlation is actually much more useful if you are looking at cross-sectional features, because at the end of the day, we are going to trade on the relative ranks of these equity rather than their absolute correlation. So you can just pass it here. There's a, I think, parameter called method, and then it will call, I think, Spearman is the name. So if you see that it has actually changed few values. So at least in this case, I'm not really keen on seeing how they are different, but that's a one neat thing that one should know and comes very handy. Uh, Spearman is preferred in cross-sectional factors, and Pearson is okay in any way if you don't know the difference. One different thing I just wanted to point out, not going into detail, is that if you see the factor from 1 to 8 has negative correlation, although even if it is small, but there is negative correlation, which is interesting. I think there could be an argument. Somebody say that returns have this tendency of mean reverting, or it was maybe it's momentum or something like that. But can you have some indication out of these? Obviously, they're going to be more. You need more sophisticated tests than just looking at this correlation to arrive at. But it will. But if you look at even the smaller day durations, so factor one, factor two, if you remember, were 1 day, 2 day returns. And so there's an argument to make. Okay, if an index has made a return today, positive one, there's a likelihood that it might not go again. At least up to not that magnitude, it might just stay at the same place or might just go down a little bit. And that longer term, it does that. Uh, in sense, there is reversion to mean. There is reversion to is it stationary or not. So those are few questions you can think of that way. And I'm not going to digress into that position in that topic. But but if you actually start to go in that direction, these numbers will start actually make sense more. But for our case, we will just say, okay, whatever correlation is, let's just take it and then just move ahead. Uh, okay, so one more thing. So now we have our data set out. As I mentioned, that we have our target variable, which is next day return that I'm going to forecast. I have all my features from 1 to 14. Let's split our train and test data sets, because at the end of the day, we are creating a model. So what I've done is just split it. Any data points up to 2010 is my train data set, and post that is test. Uh, and then it comes out to the fraction of my test set is about 40%, which is still okay. People do 70-30, 50-50 if you have really good data set. But I think 70-30 is the bare minimum you will need. So in this case, we have 60-40, which is okay. It's doable. Okay, so the first method that I wanted to discuss today is our old linear ordinary least square method, OLS method, you call your linear models. Linear models are still very preferable. I can vouch, I think Tom would also vouch that there are billions, I would say trillions of dollars getting created just using OLS. It's uh, it's true. Like we want to like say that, oh, we are using sophisticated models, but at the end of the day, people still use linear models. They are easy to understand, easy to convince to people to put money on the line for OLS. If somebody does not understand something, it's really hard for to convince them to put their money in that strategy. So in that sense, if you don't know OLS but you know all sophisticated things, you're lacking something, my friend. You get your basics first and then go and conquer the world. So what OLS actually does is that it's a simple model. We have an intercept, which is we are going to say that there is, which when I'm going to forecast everything, I'm going to say that there is some constant bias to everything. You can think in that way. Plus, there is going to be a variable one, variable two, variable three, and then there is a beta component added to it. And my Y variable is effectively the target I had, which is the next day return, and my features are the one we have created just now. The simplest way to do it is just use the packages. So I have used stats model. So stats model is we have imported it at the top. It's stats model itself is a package. I think if you're using Jupyter notebooks in Google Cloud, it will come as pre-install. You don't really need to do that. If you wanted to use linear scikit-learn modules or linear modeling, linear regression, you guys use that. But I will show you why stat model is preferred if you're using linear models. Because the great thing about stat model is I think it's written by statisticians, not by like so-called machine learning enthusiasts. Because being a statistician, you actually want to look at significant testing, like p-value and all those things. So that really comes inbuilt in stats model. Uh, and if you are going to linear regression, you would have to actually do cross validation or some other kind of metrics. You would have to define it. It's all there also. It's not as easily as just typing model.fit.summary. So okay, so as I said that we have our Y, which is we take it from which is target. We have our axes, which are the features. So if I just show you what factors I mean, so factors are effectively from fact 1 to fact 14. Uh, okay. One interesting trivia I will show is that, so rather than actually naming these factors, so I've just mentioned them 1 to 14 is that if you have ever have actually looked and spent time looking at the data science competition that are, let's say, happening on Kaggle or some other websites by Two Sigma or some other funds, they actually disguise your features in some random numbers from 1 to, let's say, 100. They would be features like similar to this, obviously maybe a little more sophisticated than these. But at the end of the day, if you are going to look at the feature name and they say, oh, it's going to be significance not, I think then in some sense you're going to get bias. So if you're really like a data science enthusiast, and then okay, no, I'm going to vouch for my models, you didn't really need to know what the feature means. It could be something as fact one. If I not told you definition of fact one, You would not know if it is a significant feature or not. And that's the idea of naming these features in the disguise form, just to give an idea that people do that. Uh, okay, so now we have our X's and Y's. Start model is easy to use. You load the starts model package. There is a package, there's an internal package is OLS. You put X and Y's, you say fit, and then you got a summary. Voila, there's nothing else you need to do. It's as simple as that. Now, when we have an output, we how do we actually try to gauge the importance of an OLS? The way we do it, we look at two, three matrices which are very easy to understand and to probably explain to someone. The first one we actually look at is the R square. It's mathematically you can say one minus the explained variance by total variance, something like that. But let's just say it's higher your variance, the R square, it's explanatory power. If it is closer to one, great, you have nearly explained all the variances in your data. If it is very close to zero, you are probably like doing a very bad job. R squares are a great way and easy to explain matrices. That's why at least I love it. But it has one limitation is that if you keep on adding more and more features, your R square actually will keep on increasing. But that does not mean your actual model has improved in its in explanatory power. So you start to look at something called adjusted R square. It in how it does it, let's not worry about it. But adjusted R square actually take care of that biasness of increasing a model. Sorry, increasing a feature or number of features in your model. So if increasing a number of features increases your R square, but decreases your adjusted R square, it knows that that feature is not adding any additional value. It is just a noise. It making me feel it that I'm adding value, but not. So as a rule, just always look at adjusted R square. There will be cases where you might need to look at R square, but for model comparisons, you can just look at adjusted R square. AIC, BICs, let's not worry for now. Other thing I just wanted to mention is that there are things which are like skewness, kurtosis, and conditional numbers that you can just look at and try to see. Conditional numbers are something like that. So there is an assumptions in OLS model. Yes, here I put it out. So yeah, how to judge the performance in OLS model that's we're talking about. So adjusted R square is a model. Higher the adjusted R square, greater is the model. Okay, correct. Second thing is that you actually look at the T stat. So these are like the T stats you get. The coefficient is the one, the betas we have got. So these are going to be our betas. Beta 1, beta 2 is this minus 0.004, 3.78 minus 3.78. So these are my betas. T is actually T statistics. And that's what I was saying, that stars module is very helpful. It directly gives you T statistics. You don't need to worry about writing an additional code and the P values. So if you have actually read any quantitative research paper, this table is what they produce in the paper. At the appendix, there will be like 4 or 5 tables like this, with T stat, this, that, significance level, all those things. So now you know how to produce it. And if you want to publish a paper, just know how to use stars model. That's that will actually help you a long way. So the other thing I was mentioning is that T stat. So T stat is a very useful metric. I really love it. It's easy to explain to investment committees also, so that higher a T stat, greater the significance, or I would say importance, the feature adds in the model. It's more significant, statistically significant. That's the idea. If it is greater than 3, great, you have really found something. If greater than 5 or 6, it's likely that it will persist in one way or the other, even if you change your model some way. So that's really good. You find any research paper which has a T stat of range from 3 and above, just barely. So I will no share one anecdote with you, is that whenever we read research paper, if there's a factor they have, if a paper has claimed we have found some financial anomaly, and it has said that the T stat is, let's say, 2.5 and 3, because if your factor has a T stat of less than 2, no research journal is going to publish that paper. So people actually fudge numbers and like do things, and then so that it means the bare minimum cutoff.
Hey, Shivam,
Sure.
just a quick question.
Yeah.
With the negative T stars, does that mean they're also significant, but in the reverse way, or is it just that they are much, much lower and they're totally insignificant?
Yeah, sure, Prem. So, Tom, in that sense, the T start is what you look at is the absolute value. Although your point is correct that a
Yeah.
negative T stat mean is that the coefficient is negative.
Yes. Yes.
It
Okay.
and so that
Mhm.
in that way it means yes the other way around.
Yeah.
But T stat is look at its significance. So higher the absolute value of T stat, it's more significant. It
Okay.
might increasing that variable might decrease or increase your output. That could be the other way.
So
But if
-5 is very significant as well.
yes, so if
Okay.
you look at the p value,
Mm.
it's like literally zero. There are three zeros. So
Okay.
it's of highest. So
Yes.
in this
Mhm.
model, fact one, fact two, and fact three are of
Yeah.
highest significance.
Okay. Okay.
That's we can say clearly.
Thank you.
Okay. It actually leads to another good point I wanted to mention is that the conditional number, if it is too large, it creates and causes some issues. Okay, so it kind of starts to say that these factors that you have thought are good factors, they are good, but then they are correlated, and you can see in some way these plot have tried to show. Okay, so the issue is that if you just start to look at factor two and factor three, okay, see them, they are literally the same but with opposite signs. So what model is actually trying to say is that there's one of the limitation of the OLS is that it needs the factors to be independent of each other. That's our basic assumption. They have to be, but in this case they are not. So what it has done is that it has conveniently learned that okay, I'm going to give positive weight to another factor and then negative to another one, so that when they get combined, they cancel each other out. And so when they're canceling each other out, they are coming to be significant, obviously, because they are not adding any value in that sense. And not adding value or constant adding a value is somehow is coming out to be significant in that way, because it does add value, but it loses its purpose. That's not the idea that we want. That's why the conditional number is large. I will still make an argument that even if the conditional number is in power in thousands, let's say, so this is because in thousands, it is still acceptable in finance. But if it is very large, 10 to the power 6, 7, 9, then you have really screwed something up. So, so even in practice, I've seen up to 1,000 it works. Like there is no way we can mitigate everything, but still, it just makes sense. Skewness has to be zero. At least uh, that's the goal while creating a model, because skewness, we assume that, so this skewness and kurtosis are for our errors. Let's say, because when we have fitted our model, okay, this model will have prediction. So internally, while fitting it model, it actually forecasted what the output it is going to have. It has taken that error. Okay, I have here it says. So what I've done is that okay, I had this model OLS. I can predict it. So this prediction is going to be something like a series, because for each date now I have one prediction of return on that day. And if I just uh, take a difference with my actual return on that day, this becomes my error. I think that that's intuitive to know. And I've just plotted that histogram here, and the idea is that the error statistics that these are shown here, these are the error statistics of this error itself. Okay, and then so our assumptions is that when we are creating OLS, that these errors are homoscedastic, they don't have any variance, they have a constant they have a constant mean, and sorry, they don't have a, they are literally a white noise. That's the idea. So they should have a normal distribution. That's in simple way. So skewness should be close to zero and kurtosis should be close to three. Normal, that's the normal distribution. But if you try to plot them to see, you can use data frame has this feature which actually produces a kurtosis function and then the skewness also. You see that it's 11 point and then plus 0.041. It's the same numbers what I hear. I'm just trying to show that these skewness and kurtosis are for the error terms. And if they are closer to ones you have for a normal distribution, the more confident you can say that your assumptions of OLS is actually not violated when you were creating that model. At least it's 11. It's in some sense I can say it's still acceptable. Probably not 100 or 200 of a kurtosis is like what you have done done with the model. So yeah, so that's just one thing. Now, if I think about that way, there could be an argument to make that how to think about improving this model. Let's say if I have to improve this model. As I said, that adjusted R square gives you the explanatory power. And at this point, the explanatory power that I have is very low. It's about 1%, 1.5 something percent. Even with high conditional number, how can I actually try to improve it? The way I can actually try to improve is that let's see if my features are actually adding some non-linearity to it. So what I mean by non-linearity is that when we had our OLS equation, the simplest one I've showed you here, there's an assumption, implicit assumption in OLS that these betas are effectively of order one. If you don't know what other order it could be, it's good that you don't know that. But the idea is that betas has to be of order one. But these variables that we have, which effectively these are factors, they can be anything. So I could actually replace this fact one by 10 of fact, sine of fact one square, fact one cube, log of fact one. And my assumptions of OLS model will still hold. Whether that model will come out to be useful or not is a different question. But can I do it in an in OLS framework? Yes, I can, and that's what I've tried to do here.